Okay, so these last 2 days class, I have on there recap, which I always think about or talk about for sure. But this is the floor I consider to be yours. So any questions that you all have from the specific, I can't do this problem, to the more general, I'm struggling with this type of problem, or I didn't understand the differentials or whatever it happens to be, that can certainly take precedence. While you're thinking of questions, so let me ask you some troubleshooting stuff. So maybe I won't even look at it. Suppose I gave you a second. Okay, so suppose I walked up to you on the street. My question is not really to solve them. Here's just kind of a troubleshooting question. What techniques do you think would be best to try on this? What do you want to try first on something? Right, what's the general technique to reflect the law? So I'm just looking at broad strokes, like parts versus substitution. Uh, what about this one? Actually, that may work. I think probably u equal x cubed, I think is going to work out well for me. Can anybody look at that and tell me why did I know that u equal x squared is probably going to pay off? I don't care so much about the three, I care mostly about the power, right? And so the hardest part of the u substitution is getting usually you start with u and it's like, okay, I know where I got my u, it's the argument of exponential. The hardest part about the u substitution is getting the du fit in. That's why I often, if I can write the u substitution as x equals, then that's usually instead of u equals some function of x is a function of u. What tips me off is that x squared dx, from the perspective of power, is perfect for the du, but it's 1/3. So I think this one's better. What about this one right here? Right, what substitution would be good here? I agree. Because in this case, du is x 1/2, that's the minus 1/2 dx, and this bit is essentially your du, and then it's even u, right? So pretty good there. How about this one here? What technique do you think you do this last? I agree. I agree. Do you know there's something special that's going to happen in this one? You, you know, get down the road for it. Yeah, that's right. This one is like one of those, tail chasers, right? Where you do it a couple of times and then you get back to where you started, solve for it out correct. So when you, the more homework practice on this, that's one of the things is figuring out what you want to try to do quickly. I mean, usually my first instinct is if something jumps out at me, like a log, an inverse trig function, something like that, then maybe I think parts. But I usually look first and say, is there a substitution that will make things better? And again, a substitution, sometimes a substitution, uh, sometimes it will require multiple substitutions. There's nothing wrong with getting yourself partway down the road. So for example, solve it like this. This one. Yeah, but I mean, you have to take that to look at 3/5 power, right? Go S one third S. But your thinking is along the right track, yeah. So here's my thought process. This X to the 1/3. So now this is going to be an integer power, no more of that fraction. And the idea is, of course, 15 is a common multiple, both 3 and 5. And so I can now write this. And actually, the best thing in the world is to write this way. That makes it easier. So this becomes the x is 15 u to the 14 du. See how easy that is when instead of trying to figure out how to plug in u, when you just write the x. I think that's why if I can get it in this form, I'll do this. And this is u to the 5 plus u. Where is it from? Okay, so now here comes the silly part. By the way, is there something I can make this look really? Great. Like there's a common factor u squared, so let's make it look a little bit. Oh, actually, u cubed on that. So u cubed, that's down to 2, and that's down to 11. Now, I can divide u to the 11 by u squared plus 1. do long division, but I'd rather not. Right, because my first term will be, if you divide, you square plus one into U11, so if I were to go through that process. And I could, just. But 0, 10, 0, 9, that's the point, I guess. I'm gonna have to do a lot of division, right? It's a long division. I'd rather not do that. Avoid it. See, what see substitution? I'm gonna eventually have to do some food. Or something like that. See, this is substitution. There's substitution of the soup. See, we've already done one substitution, but. Somebody tell me why this. Well, let's get the part. So. Account for that, right? That's the whole point. What about that U to the 11? That looks complicated. How's the substitution going to help you think this? At the top is 15 U to the 11 U, which is 15 U to 10 U. What about, I've got this taken care of, my UDU is taken care of here, right? And remember, you've always got to have a DZ in there. You're always gonna have to have that DZ. What is unaccounted for? What is left out? Basically 10 powers of U, agree? Can we take care of that? U to the 10. So now, let's see what this becomes. This is 15, U to the 10, this mess. U to U, this mess. And then I get just. This is, I'm gonna pull this 15 halves out, let's make it. Yeah. So this is 15 halves. I'll do the multiplication. C5 minus 5 is 4, 10, 3 minus 10 squared plus 5, C minus 1 all of them see. Now that I've multiplied out there, I'm pulling this in the top. What should be next? What should I do? Split it up into pieces, dividing, so this is 15 halves times the integral of C4 minus 5Z cubed plus 10Z squared minus 10Z plus 5 minus 1 over C. Now we begin the long journey back. Well, so this is 15 halves times Z5 over 5. It's 5 fourths C4. Plus 10 thirds Z cubed minus 5Z squared plus 5Z minus natural log absolute value. Thanks. Two. 75 halves squared, 75 halves, Z times 15 halves, natural absolute value, let's see. This is the answer, but it's in terms of Z, I think we might not be variable. So let's go back here. What we see? It's U squared, right, it's U squared plus 1. So where I see the Z, I'm gonna put that in. F plus 25 U squared plus 1 cubed minus 75 halves U squared plus 1 squared plus 75 halves U squared plus 1 minus 15 halves natural log U squared plus 1 plus, and in the final step, you need to go all the way back to the original variable. And what was U? U was x 115. So U squared show up. So this becomes 3 halves x to the 2/15 plus 1 to the 5th power minus 75 eighths x to the 2/15 plus 1 to the 4th power plus 25 x to the 2/15 plus 1 cubed minus 75 half x to the 2/15 plus 1 squared plus 75 halves x to the 2/15 plus 1 minus 15/2 natural log x to the 2/15 plus 1. Now, I hope this also shows you some of the raw power that substitution has, because look at this mess. Probably nobody's guessing that when you take the derivative of this, that's what you're gonna get. Right? If you take the derivative of that huge mess, which is a bunch of like chain rules, when all the smoke clears, the derivative of this is 1 over the cube root of x plus 50 x. But also the moral of the story is, notice we didn't build Rome in a day. This first simplification, or this first substitution, gave us something that we could wrap our heads around, but then we had to do another one. Now, it is true that we could have done one substitution, basically if you compose it. So if I did the substitution, z is, do you all see where I came up with the substitution, x to the 1/15, the logic behind it, that these are both integer powers of that. But how many of you are going to guess the right substitution, just to get straight to z, would be the substitution z equals x to the 2/15 plus 1? Nobody's guessing that. I'm guessing, right? Where in the world would you get that? But this is what the problem would be, because if you do this substitution and this one, that's what you get. So don't be afraid of, taking a little piece, right? Don't feel like you're going to solve the problem with that first substitution. Just made it easier and made clear what the next substitution, but made clearer what the next substitution. Okay. Questions on that? Right. How do you all feel with the homework and all doing doing the feel like you're making progress with that? So what's the sticking point for you? Is it right at the outset where you're not quite sure what to do, or
A little bit, like, I haven't been able to do it on my own without looking. I have to constantly. Struggle.
might make? See, I'm not even sure what it was. It's just parts. It's a substitution. Well, I mean, I'm not even sure what the derivative that's the x is without doing some kind of algorithm differentiation. You might write this in an easier form. Look at the x to the x. Variable base, variable exponent. How do we always conquer? When I would ask you to take a limit or a derivative or something like that, what's almost always what we did here? There's some kind of log. So let's do this way. Those two are the same thing, because the log and the exponential is back to the original. And this is e the x log x. So x the x is this thing right here. the whole point of this being log, because now you know what the variable rates and variable x are. What do you want to try now? It's what you're first. Yeah, I think I want to trust about, and here's why I want to trust something else first. Okay, so I don't think I can use this report that I can integrate, because I'm not sure. What the heck that is. And I could figure this one out. I could figure out the antiderivative log of one, but I'd have to use parts, right? So that would mean that my dv might be just dx, but then I have to take the derivative of this as product rule. It's gonna make a big mess. Probably u-substitution. What might you try if I said try u-substitution? But problem log, so derivative log is one over x, right? There's no one over x in there. You're close. We trust the simple approach. Always try simple. Sometimes arguments are functions. And you'll see the setup there. Let's try the exponent. Derivative of this is what, product rule? So it's derivative of x, 1 log x. This x times derivative log x, well, I smell the setup, right? Of this. This e to x log x plus c, or if it's to your face, and derivative of x. So this function on the bottom is x times the natural log of x times the natural log of the natural log. I want to find an answer. I'm gonna try u-substitution first. Here's why. Here's a mistake not to make. I've seen people write parts and they'll say dv is dx and u is x log x log log x. X log x log log x is not a part of this. It is 1 over that. So let's see, u-substitution. Okay. So. U here. What is U? Well, don't forget that. That plus one's killing me. I don't know. Certain. I don't think we want to go this way. Let's trust it. Yeah. I want to take yours and back out a little bit. What you gonna do? Yeah, your idea is really good. What's the root blah blah guys? Well, it's changeable, right? So first thing I come to is rid of the blah blah. Root blah blah is. But I'm not done. I've got to multiply by the root of what's inside there. What's the root of log x? Number x. Then dx. Oh my goodness. So what have we got? It's u in the bottom. And it's dx. The anti-derivative one over u. U, let's see. So I get log absolute value log x. Other things would harder. And this goes into my theme of, you don't have to worry about. Eli actually saw the best substitution, perhaps, except for maybe. The very best substitution, like did log things. But if you saw that, you just put it's a derivative log x. But you might have done this, done something more naive. X, log x, log x. You might have said to yourself, I just don't know, but let's do this. I see an X there. You might have done this, right? And now this piece is the U. There's a U. And there is log of U. Agree? And although I haven't really solved the problem yet, it certainly is better, isn't it, than the original. And I said, hey, you know what? Let's go back to the well. Let's do this again. And now U over U is dz. And this is, so I get natural log absolute value of z. Let's see. Z is log U. And U is log x. So this substitution didn't quite have the cleverness that Eli's substitution did, but it gets us there eventually. So often there are multiple ways to do this. Okay, any questions? What do you? What might you do? Good idea, right? Inverse trig functions, things like logs, inverse functions in general. So let's try this. If we do parts, which sounds like a good suggestion. What's the biggest, ugliest piece of that you should integrate sort of in your plan? Well, yeah, and that's kind of the point of this, because I don't know the antiderivative. Because it is right, but I do know the derivative, right, and I think that's the point you're speaking to. So what's the biggest ugliest piece of that you can integrate in your head? But again, if you could do that, why don't you just write the answer? Nope, that's inside the function, so you can't muck with that. That's a composition, so that's not inverse sine of x times 2x, that thing's actually something. There you go, I mean, that's it, really, dx. And the other piece, the inverse sine of 2x. Now, at this point, this is a good gut check that I mentioned to you all last time. The UDV, when you put these pieces together, you should get what you're integrating. These two, the product of these two have to be this. Otherwise, not done partially. But as long as U comes dV, what you start with, and there you go. Now let's figure out the other pieces that we need to know to make this work. V is x, right? Du might be a little help on that. What's the like square? Square. One minus, well, in this case, what is it? Right, so it's gonna be like 4x squared, right? Because you're going to actually square the two of things. But okay with that? Times what? Which is 2, and don't forget your dx. So that's what I got. Everybody okay with that? So it looks like parts are starting off rather well. It's the product of these two. Minus the crossing. So I get like 2x. But now what? So right here, I've kind of mentioned a conflict. What u-substitution might work well. Perfect. Yeah, that one couldn't be better. Let's do this. And of course, a dead giveaway is I've got 1 power of x on the top. When I take the derivative, that is going to be 1 power of x. It's going to be a match, so it's going to work out well. So, x inverse sine 2x minus interval of, well, let's see, it's 2x dx is minus 1/4 be u. And on the bottom, I guess I get u to the 1/2, don't I? Okay, any questions? This is just coming out of. Really, we've got a whole lot of horns now. That's gonna be 1/4 plus 1. Yeah. So this becomes x inverse sine of 2x. That's 1/2 u to the 1/2. C. One half u to the 1/2 plus c. And now, just remember what u is. X inverse sine of 2x plus 1/2 of 1 minus 4x squared, 1/2. Again, I mean, I think this is a worthy exercise if you look at all the problems. You can always forget the back of your book. And in fact, oftentimes, how many of you look in the back of your book for the answers? Check, right? If you have a problem, and do they have like the odd answers in the back, or something like that? Well, especially if there are things like logs involved in the answer, there are many, many ways to write these problems. And they read right. You can always check this continuum derivative of this and see if you get back to the original function. And sometimes, if you're not comfortable with parts of this, you can see the thing put back together. You can almost see u-substitution working itself back into the derivative. Okay. Question. Okay, other questions? I don't know if I addressed your concerns by not going to so
It's a little bit better. It's really just something I have to like look at. Now it's like a memorization.
well, I mean that's what I mean. It's, I would say less memorization, more just shooting foul shots. Right. Just gotta keep doing it. Okay, here's one. How many of y'all live in an apartment? You got a couch in your apartment? You have to move that thing in? Everybody, I think everybody that's been in college has been through this. Follow. Idealize. So 6 feet, 9 feet. So, two people are moving straight and cold down a 9-foot line. All of them. They have made a right turn down a 6-foot line. What is the longest length of pole that will fit around the corner? Now, this is a practical equation, or this is a practical problem. But let me also point out some shortcomings from practical. So these two people were carrying this pole, and like I said, and they've got to get this around the corner, right? They're trying to go from this maybe main hall into a smaller hall. They've got to get this pole around the corner. And notice that there's sort of the longest length of pole that you would expect to fit. Now, like I said, this is a problem that almost every college student who has moved into an apartment or a dorm has encountered. When you try to get your furniture or something in there, you know, you're coming up the stairs, you're going around the corner, everybody's weaving a tapestry of profanity because it never seems to quite fit. Now, what is idealized about this problem is what is less complicated problem than what you've had to deal with. Is number one, I'm assuming that you're going to put a pole instead of a sofa in your apartment, right? That. And number two, what other assumption am I making? What's another practical thing that you could do to get a bit of a longer pole that my drawing seems to imply that I'm not considering? Well, right. So when you try to get your couch around the corner, right? First of all, the couch has got thickness, which complicates the problem. But also, what happens when you're both pushing the couch along the floor and it doesn't fit around the corner? What does somebody do? Well, right, you could try to rotate it, but even if it was a pole or something else you could do, you could kind of go on the corner. Somebody lifts it, right? I mean, you lift it and change the height, you try to get more space that way. And we're ignoring that possibility too. These two poor souls look flat. So we're trying to get it around the corner. So does everybody understand the problem, right? Notice that here, notice that this pole looks like it's a little bit too long to get around the corner, right? And of course, a pole that long, I could easily get around the corner. So there's some length of pole that's as big as possible to get around the corner. Everybody agree? First question, is this a math problem or a mental problem? Seems like it. But actually, I think that's a mental problem. Because the longest length of pole that you can get around the corner is the minimum distance red like that. So whatever's the smallest red line I can draw is the biggest pole that you can get around that corner. Right? So what I want to do is I want to minimize the red line. Because the smallest length I can draw with this triangle around the corner is the same as the biggest length pole. Okay. How do we even go about this? I'm going to explain this. So I'm going to call this theta. I'm going to call this L1. That is the length of the pole from where it hits this corner over here. And I'm going to call this L2. That's the length of the chute here. Right here. What's this angle here? It's the same as theta, right? Because these are two parallel lines of transverse, right? There's other ways to do this, but these two lines are the same. Right? Okay. All righty. So let me break this down into pieces. What kind of things we want to minimize? Trying to find the minimal distance across the corner L1 plus L2. Now, I don't have a good feel for L one and L two, but maybe which my variables. Right, whenever I do a max min problem, there's always something that's changed. Now, maximizing and minimizing, when I do a volume or something like that, there's always something that's varying that changes the volume that I'm looking at. That I'm trying to find. What should that variable be? How about theta, right? Because theta varies, right? I mean, as the guys come up the hall here, theta might be very close to pi over two. And as they try to work it around, and of course, if it gets all the way around, theta can go down to zero. So theta varies as this, as I change this length around the corner. That blue length right there, 6. This length right here, 9. So can somebody give me L1 and L2 in terms of theta? What's L1 over 6? Right, so it's hypotenuse over opposite. It's the cosecant. So, in particular, L1 is 6 cosecant theta. Correct. Same kind of trick. L2 over 9. What's that? That's going to be the secant. So this is definitely a step forward. Because now I've got something in my hands in terms of theta. So let's recap this again. We're trying to minimize L1 plus L2, which is 6 cosecant theta plus 9 secant theta. That's the function we're trying to minimize in terms of theta. And this is especially important in these problems, which should be the next thing we'll be doing on max min problem. Good, good. We need to find out what is our playground for theta, right? Well, remember what this does. This represents, well, small. Think about it this way. 6, 9. There are lots of ways you can get around the corner. You lay the head down here. This. You're a little bit more up here. This. This. Maybe that helps you. So here's my theta here. As this gets longer and longer down the hall here, what's theta getting closer and closer to? Go further and further down the hall. What's oh, 2. But it never quite gets there, does it? And again, a good hint for this is secant's got a problem with power 2. Now, once you get the bar here, you know you can go down the hall. What is theta getting closer and closer to as you get right up toward where the doorway is. 0. But never quite there. And again, cosecant has a problem with 0. So my playground is, as we're bringing this thing in, theta goes from very big, very close to pi over 2, very small, very close to 0. Right? So this isn't one where we can plug in the endpoints, we're gonna have to determine what we can match them. So we'll call this just L for length. Okay, how about you? Let's do the part like this easier. What's the derivative of secant theta? If I remember what the derivative of cosecant is. Good for you. Cosecant theta cosecant, that's right. And again, if you're ever in a spot, secant is, I'm sorry, cosecant is just one over sine, so you could just find the derivative that way. You can use the cosecant. Now, this is confusing my piece of the brain, so I'm gonna write this way. This is -6, that's 1 over sine, cosine over sine, so -6 cosine theta over sine squared theta plus 9 sine theta over cosine squared theta. This helps me see critical numbers a little bit better. I see that I've got a critical number, well, I've got a potential critical number of 0 and power 2, but hey, it's not in our playground, so we don't have to worry. So the only possible, when 0 and power 2, these denominators are always not 0. So the only thing I have to worry about is when this is 0. So let's set the C equal to 0. See what comes out of this. So in my next equation, I will get 9 sine theta, cosine squared theta, is equal to 6 cosine theta over sine squared theta. So let's see. Gosh, what a mess this is. But here's what I'm going to do. I'm going to manipulate this a little bit. I'm going to take cosine over here. I'm going to take sine squared, cosine, so 9 sine cubed theta over cosine cubed theta is equal to 6. Sine cubed, right. So I get sine cubed theta over cosine cubed theta is equal to 2/3. 6 times. And this is tangent. This gives the only proof. Let's solve this. Tangent theta is the cube root of 2/3. Or theta is the inverse tangent of the cube root of 2/3. And you all know what that number is? That's a trick question. The number is the inverse tangent of the cube root of 2/3. That's it. In fact, that is correct. If you put that into your calculator, no matter what your calculator tells you, correct. This is absolutely. Okay. What do we have to do now? We found one and only one critical number. What do we need to do? Like, we need to plug. So, well, before that, we need to check if this is a minimum. Because that's what we're going for. Well, I'll just draw a number. It's pi over 2, 0. 0 playground is just in here, right? It's on an interval. The problem is it doesn't have the input, so we can't check. And in here somewhere, I have this critical number, which is the inverse tangent of the cube root of 2/3. My goodness, how do I tell the sons? Let me remind ourselves what the problem was, what that stuff was. That was -6 cosine theta over sine squared theta plus 9 cosine theta over sine. Right, I mean, all I gotta do is, I mean, I'm not even quite sure what this number is, so, you know, you can let the plug in number. How can I tell whether it's going up or going down, whether the derivative is positive? Right? One of the things that when you're science here, what to do is be able to do kind of a field estimate on something. Let's think of it this way. What happens when L prime is I can't plug in 0 to this thing, no problem, but I can get close to 0. What's happening to this thing when theta is close to 0? This piece right here, cosine squared theta is very close to 1. Sine theta, since theta is close to 0, is close to 0. Whatever. So this is almost up there. What's going on with this? This is getting huge, right? Because the top is getting close to -6 and the bottom is getting close to 0. So it's -6 divided by 8. It's a tiny number. This is a huge, huge negative. Ready? Let's check the other side. What happens when you get very stinking close to pi over 2? Well, now this thing is very, very close to 0. Because if pi over 2, the sine is 1 and the cosine 0, this is almost not there. This is getting to be a huge number and it's positive. So what happens here? It's a relative minimum, that's for sure. It goes down and up. So this is a minimum. And it's the only critical number. So on our domain, it goes down, it hits that minimum, goes up forever. So this is an absolute. Everybody okay with that? Okay, and did I ask the question about what is the longest link pole? Okay, would everybody agree that at this critical number we get, that's the smallest distance around corner, so that's the same as the longest pole. So what's the longest linking pole? I'll show you how you can get it. You can plug this into the calculator, but I'll show you how you can kind of get it in close form. Like so, pole longest, and then theta is equal to the inverse tangent cube root 2/3, right? This is a useful trick. You will see this in 1080, especially when you get to trig substitutions. So I'll familiarize you with it as much as possible. So what do we have here? We have theta is the inverse tangent of the cube root of 2/3. That means the tangent of theta is cube root of 2/3, right? So just build your triangle that way. Let's call this theta. Right triangle. This is the cube root of 2/3, and this is 1. That's the easy. All I have to do is make this ratio appropriate. Cube root of 2/3, 1. That's the easiest way to do this. And what's the missing side? The missing side is this square plus this square, square root. Let's see what I got there. So now all you gotta do is plug in here. L is 6 cosecant theta plus 9 secant theta. So just read the triangle. The cosecant is hypotenuse over this, so it's square root of 1 plus the cube root of 4/9 over cube root of 2/3. And 9 with the secant of theta, which is this over this, which is square root of 1 plus cube root of 4/9. So there is the longest in feet. That's the length of the longest pole that those two posts can get around. Any questions on? Okay. Uh, yes. So I'm gonna actually give them a minute to work on this. I'm gonna do this actually. Take a minute to see if you can figure out. You know what this looks like, or what's trying to do? That's the key to it. I want this actually a couple of legs that are very intimately related. Here's sort of the algebra too, like, do. I think I'll be completely obvious what this looks like, but if I square both sides. Right. See what I can add to this piece right here. Make this a perfect square. Back in the old days now, we're completing the square. Anybody know, if I remember the trick, what do I add to this? Well, that's a perfect square. What is X minus one squared? If I agree with that. And remember, if y'all remember the trick, is you take half of what's multiplying the X term and square it. All right, does that ring a bell? Now, this salad was, if I added one over there, I better add it over there. And this is y squared plus X minus one squared. Somebody describe to me what this curve looks like. It's a circle. Radius one, where that centered at 1, 0. That's what the whole circle is. But the original function was just the positive square root. So really, what this is saying is this is 1/4 circle area of radius, in this case, 1. So it should be 1/4. I said you do a u-substitution, and that's true, but it's almost equivalent to doing this. Here's another way to do the problem. And this is why if you did what would probably occur to you naturally during the substitution, you probably didn't get anywhere. First, I'm going to do kind of a trick like I did before. Right, that's the fancy swell in the world, but see it. What's the point of this? This now becomes one minus. Check this. Here's my 1. I'm gonna have a minus x squared there. I'm gonna have a minus 2x there. I'm gonna have a minus. Now on this one, do the substitution. U equal x minus 1. So du is dx. And this now becomes interval of the square root of 1 times squared. And what are my new limits? What's my new bottom limit? That's right. In the old days, X is 1, in the new days, U is 0. New top limit. In the old days, X is 2, in the new days, U is 1. And this one's a little bit easier to see. This is a circle, radius 1, and you're integrating it 0 to 1. So this is 1, 4, 9, 1 squared. Same. Okay. Any questions on that? I saw a problem in textbook, which I thought was kind of interesting. Apparently it's called Kepler's wine barrel or something like this. So there's a story with this. Apparently, they used to sell a mouse of wine. They would take a dipstick, stick it diagonally for some reason into a barrel of wine, and use the measure of that to say how much this barrel of wine is worth when you're buying wine. Apparently, Kepler realized that this didn't really determine the volume of the wine in the barrel, the sleeve. So if this is, let me make this count. If the space maximize all so this would be the radius of the barrel. So the only thing the dipstick's doing is making this diagonal distance down the corner. With this fixed value of D, what's the ratio of R to H that makes that volume maximum, right? Because D could be, of course, D could be like we've seen before, it could be, you'd have the same D on a very short, wide barrel or a very tall, skinny barrel, and which one is going to hold the most wine? Okay, so how are we going to approach this? What's it? Find R over H when the volume is max. So that'll give you kind of a ballpark, right? So if you want to make sure that you're getting the most wine, the answer of radius to height is going to tell you. So if R over H is, for example, 1, what you're looking for, if you want the most wine, is a barrel in shape so its radius and height are about the same thing, right? And if you say, for example, R over H is 2, you want one that's like wider than it is tall. If it's 1/2, you want one that's taller than it is wide, right? So how are we gonna figure this out? I guess we can start with what's the volume? What's the volume of the barrel? Right, it's the base times the height, and then you kind of, cylindrical kind of thing. Base times height, And in this case, the base is pi r squared, because the base is a circle, times height. And we run into the problem, we always run into, almost always, these kind of things. I got too many variables, so change the R to take 8. How am I gonna balance these? Right, I don't think we want the area though. So what equation relates to DHR? Magnitude. So we also have D squared is R squared plus H. And remember, the R and H, they can vary, but my D is fixed. D is just a number. Might as well be 27. Okay, folks, what do you want to do? You want to solve for R or H? Which one's going to be easier? R, I agree. What is it that sets you off, that lets you know that the R strategy is going to be better? Because R is squared. If you solve for H, you put it back in, you're going to have to do a square root. That'll work. You can try it if you want to get really strong with derivatives, but I'm a lazy man. So I would rather replace the R squared than one. So this gives me R squared, D squared minus H. And I'm going to use this, plug back in here. So I've got a new improved volume. D squared minus H squared. Which is, you know, write it this way, pi D squared H minus pi H cubed. And what else should I be doing, thinking about doing at this juncture? Right, my variable is H, good. I want to range for H. How small could H be? I guess it could be 0, really. There's nothing here that violates it. I mean, my volume's going to be 0, H is 0, so that's kind of bad. But how about R? How big can R be? H can be a smaller piece. I don't think R. How big can H be? I don't see any limit to how big H can be. Oh, right. H is as big as possible when R is what? So how big can H be? If you stretch this up, H is closer and closer to. As R gets smaller, H gets closer and closer to D, doesn't it? Right? And if you look at this equation here, as R gets smaller and smaller, then H squared and D squared should get closer and closer together. So, and again, I think that if H is equal to D, then you should get no volume out of this. But you know, it's doable. There's nothing in the equations to solve. You know, I'm liking this problem because it's continuous function. So let's take the derivative of this. Take the derivative of this one. I get pi squared minus 3 pi H. And I separate this because there's nowhere this is polynomial. There's nowhere this is. So in solving this, I get 3 pi H squared is pi E squared. So if H, let's solve this out, is D over squared. Now, this is a continuous function on a closed interval. I'm digging on that because now all we have to do is just check points, right? We need to check D of zero, one of our endpoints, B of D, our other endpoint, B of D over the square. B of zero is zero, that's an H of zero. B of D gives you a zero as well. I'm plugging H of D. And B of D over radical 3, as long as it's 3 over 0, it's our maximum. That's going to be D squared minus a third D squared, it's 2/3 squared. Times H, which is also D over 3. And I don't really care that much about this number. This is 2 pi over 3 radical 3 D cubed. The only thing that I care about is this 0, and this gives us our max. That is the maximum amount of volume that barrel hold. Now the question was find the radius, or I'm sorry, the ratio of R to H. H was D over the square root of 3, and R using this equation again, figure out what R is. I get R squared is D squared minus a third D squared, which is 2/3 squared. So R is square root of 2/3 D. So R over H, which is what we're being asked for, radical 2/3 D over 1 of the radical 3. And the D's cancel as they should, because it shouldn't matter what the length is, that proportion should be the same. So the D's canceling makes plenty of sense to me, and I get the square root of 2. So that means that the ratio of R to H has to be about 1.4-ish. So actually you want a shorter, fatter barrel for more line. Okay, any questions? Okay, so I'll give you the quiz for today. You can turn it in when you're done. Do some homework tonight, bring me some questions tomorrow. We'll have more kind of review. I've always got stuff to talk about. If you don't have questions, I encourage you to bring them. And we will also have, tomorrow will be the last day of class, but we'll have a review session Wednesday at 5.